In this video, we're going to apply our new amplifier model to the common emitter amplifier. This will give us expressions for Rin, Rout, and AV that we can use whenever we see a common emitter. However, we're going to make one really important decision about our biasing network when we do the analysis for these Rin, Rout, and AV expressions. That will help us generalize these expressions to a wide variety of biasing circuits. I've drawn a common emitter amplifier on the left of this slide, and it's the circuit we're going to analyze to find reusable equations for our common emitter amplifier parameters. However, we've made a few decisions in this circuit that are interesting. First, I've drawn a box around the amplifier to indicate the boundary of what we consider the amplifier, and what we consider the rest of the world. We're trying to analyze the amplifier's properties separately from the rest of the world to which it's connected. So that means we'll be zeroing the source resistance when we calculate Rin and AV, and we'll be opening the load resistance when we calculate Rout and AV. As a result, I've skipped drawing Rs and RL over in our small signal model, because they don't happen to matter for this analysis. That's actually a little bit sloppy of me. In general, it's best to draw separate models for calculating Rin, Rout, and AV that have Rs and RL in the right spots, but I'll comment on why Rs and RL don't affect our expressions as I analyze this circuit. Second, we've picked a very silly biasing network for this circuit. This type of biasing is both tough to implement in lab and unreliable, which we're going to talk about in the next video. But we often use this sort of stacked voltage source bias for amplifier analysis, because it means both of our biasing sources get shorted when we're doing small signal analysis. So that choice of bias lets us analyze our amplifier's properties independent of the network of biasing resistors that we're going to hook it up to. And if we have these core amplifier expressions that are independent of biasing network, it's usually pretty easy to modify them once you actually have a biasing network hooked up to the amplifier. Usually just by taking the standard Rin, Rout, and AV expressions and adding something in parallel or something in series or a little divider. Alright, so all that said, I'd like you to pause the video and use this small signal model to try to calculate Rin, Rout, and AV of the common emitter amplifier. From the small signal model, we can see that small changes in Vin are applied directly across RPi. So the ratio of voltage to current seen by this source is just set by this resistor. That means Rin is equal to RPi. When we're finding Rin, we assume Rs is 0, so I've just drawn this wire shorted, and it wouldn't affect our calculation. And technically, when we did this calculation, we needed RL in parallel out here next to RC. But common emitters are nice because the output isn't coupled to the input at all, so RL doesn't affect this expression. The voltage at the output node is given by the current in the dependent source driven through by the collection of load resistors. Driven by the collection of resistors attached to the output node. Which in this case is a parallel combination of RO and RC. This means the voltage is minus GM VBE to get this current times this resistance, RO parallel RC. Meaning that the gain overall is minus GM times the quantity RO parallel RC. RO is often much bigger than RC, so it's common to use minus GM times RC to describe the common emitter gain, voltage gain in practice. When we're finding voltage gain, we assume Rs is 0 and RL is infinite, so this circuit is actually perfectly accurate for calculating voltage gain. Finally, we shut off Vin and add a test source at the output to find Rout. The GM VBE source is forced to 0 by having 0 input voltage, so we can just kind of ignore this. Which means the output source just sees RO in parallel with RC. Technically we should have included RS in this analysis, because we need an accurate RS when we're measuring output resistance. However, all RS would have done is add a series resistor along this branch, and the node voltage here would still be 0, because there's 0 on the left side and 0 on the right side, and just resistors in the middle. So it wouldn't change our conclusion that the GM-VBE source is shut off. So in summary, we derive amplifier parameters for common amplifiers without attaching a bias network, or with this kind of dumb bias network that turns invisible. That allows us to adapt these sort of core amplifier expressions that we derive to different biasing situations or biasing networks just by adding something in series or parallel. With that in mind, here are the common emitter amplifier parameters that we've derived. Rin for a common emitter amplifier is R pi. AV is GM times RC, though technically GM times RO parallel RC. And Rout is about RC, technically RO parallel RC. And just remember that the input is small signal grounded, but not large signal grounded when we measure Rout. So we shut off the small signal V in source, but we don't hook a wire from the base to ground.